Okay, so I'm recycling here a talk I gave a couple of months ago, which is a bit of a grand overview of things I'm working on, which I thought might also be useful here. So if there's anything here that intrigues you, talk to me. This is
We're not.
all active research. So the way this talk is structured, I actually start with like some reflection on the last 20 years having been machine translation, lessons learned from that. To research into the first part. Yeah, lessons from a quarter century of machine translation research. So this is really work I got involved with on 98, 99. And back in the day, I was actually still involved in systems that were built that had rules like this. Was getting a bit more abstractive than this, but the idea that you kind of parse the content and then get interlingual representation, which are very symbolic representations, and then you have mapping rules. So this is a completely made up rule, but you basically have to come up with rules that translate ambiguous words like here the German word Bank, which could mean bench, but it could also mean bank. And then you do put in stuff like if the object of that is sitzen, which means to sit. So you sit on a bench, you don't sit in a bank on a bank. So that's how they are different. So around 2000, that were the systems that worked. So when Google Translate went online, they actually used Systran originally, and that was a rule-based system. So the revolutionary day at that point was, hey, instead of doing that and writing all these rules, which were then conflicting in complicated ways nobody could anticipate, like imagine if you have like thousands and thousands of these rules, so easily very haywire. So the revolutionary idea was, let's learn from data. So we're going to learn the word bank occurs many times in text, and therefore, and it gets translated as bank and sometimes as bench. So we're just going to learn probabilities for that. So this has been very successful. So this is a chart. I don't actually have the underlying numbers for that, but it was presented by Paco Guzman, who's working at Meta on machine translation for a long time, that kind of tracked the kind of progress in machine translation over the year, mostly based on blue scores on the WMT news translation task. And this starts now in 2010 already, but there has been fairly continuous progress over that. So this is a period that saw both the transition from statistical to neural at around 2016, and also saw the transition to now use of language models. So even in translation, so the best system you start with the last language. Here's another super interesting chart. We always got the criticism, the blue square goes up, doesn't really mean anything. Really matter later, real quality difference. So this is from a company that used machine translation internally very heavily, but it was really a human or professional translator company. So you hire translators, but they use a tool where they then either post-edit something they originally called fuzzy matches, so similar examples in the parallel data, or they use machine translation. And they tracked over time how fast the translators were. So this is a chart that starts in 2015, also goes over 10 years, also updated last year, where they measure how many seconds per word translators needed. And in 2015, it was over 3 seconds, and that now dipped below 2 seconds. And the baseline here is 1 second. So that is the time it takes. Even if the translation is perfect, you still have to read it and verify that it's perfect. So you still need at least 1 second of the time. So they always kind of drew then a suggestive line, not in this chart actually, the earlier version where they kind of looked at the intersection. And as always, it's in 5 years. In 5 years, if the progress continues, it's as fast as, just, yeah.
How fast is translating from scratch with either typing or dictation?
Heavily depends on the translator.
Yeah.
but it's
this must depend on the translator as well, right?
Everything depends heavily on the translator, the content. Whenever you get humans involved, you get huge variety. But it's basically so like 3 plus 3, 4, 5 seconds.
So even in 2015, this was faster than translating from scratch.
Yeah.
I mean, it's not obvious; it has to be.
Yeah, I think that was the first kind of proving point for machine translation in that world. That is it actually better than what they have? So the history at that point was that they actually used something called translation terminology, translation memories, which basically they stored all their previous translations they made. And then a sentence came and compared it against previous translations they made. So there are often translators that, they translate the user manuals for IBM. They translated the user manual last year or the annual report last year. Now the annual report for this year comes in. There are probably a lot of similar sentences. So if they already translated the sentence before because it was just recycled from last year, it just looked up that and didn't have to do anything. So they were already using those kind of tools. But then the use of machine translation took actually a really long time to really enter that market. The proving point was it is faster to post-edit machine translation than translating from scratch. And that started around like mid-2010s. Okay, so here's a little bit of a list of progress in statistical methods. So there's the first decade of data-driven machine translation. I'm not going to go over it. But the various things introduced, part of them are modeling, like how do you actually break, like in probabilistic models, you really had to make predictions for the next, and you had to condition it on something. What do you condition on? Matter. So for instance, with a condition on reordering, like reordering models, the operation sequence model was also modeled. Another direction was the linguistic sophistication of the models. So at some point, actually using syntax trees was actually helpful and it allowed you to produce grammatically correct sentences. There are also various machine learning aspects, like at the beginning, minimum error training, and things like minimum base risk decoding or training really fine-grained speed features, which is sparse features at the end. So all these things kind of evolved over time. All these things contributed to the progress. The other thing I like to point out, we actually used very large language models already before the neural era. So this was a language model trained on 1 trillion tokens, almost 1 trillion tokens of English that we used in one of our systems, so WMT14, as an additional scoring component. So the statistical models, it always varies scoring component, but one of the components was a language model. And here we used a really large language model. So if you actually compare that when large language models came out, they're actually much smaller than that. So GPT-2 was trained on 8 billion tokens. This is trained on 1 trillion tokens. And it's actually fairly recent that they actually now train language models in the order of trillions of tokens. Okay. A bit of a history of neural machine translation. So the first thing that actually where neural methods popped up also a long time ago was to the addition of neural language models. So these are basically just the neural versions of a 5-gram language models. So you basically take the 4 grams of history and try to predict the next word. This was especially pushed. I think it came out of speech recognition, where people also use these. They were called continuous space language models because you pack things into a continuous space. So vector representation. And again, this is an additional scoring component that proved to be somewhat successful. It's just like suddenly people talked about you need to buy a GPU, and not everybody was buying into that crazy stuff. I think the one that really made a big splash was this model, which was called the joint language translation model. So it's kind of similar to the previous one, where you addition of the previous words to predict the next word. But you now also, in addition, look at the relevant source words to make that prediction. So it was basically a language model and a translation model at the same time. Still a very fixed window size, 5 words of previous text content, output word content, and what I'm doing here, 3 words of input word content to make the next word prediction. Which input words to pay attention to was already driven by the statistical component, which also at the same time identified phrases that needed to be translated, so we knew what was the context in the source that we need to map from. Okay, the first real end-to-end neural machine translation models were based on recurrent neural networks. So the idea that you have a recurrent neural network running over the source sentence, and then you have a recurrent neural network running over the target sentence. And what connects the 2 things is the attention mechanism. So this is the first time the attention mechanism showed up. And that turned out to be really successful. That was already kind of the breakthrough for neural machine translation. So within a year, the entire field switched from statistical methods to neural methods based on this kind of model architecture. And then obviously the next evolution was the transformer model. So there was a time where you actually had various different architectures, and it seemed like, oh, there's going to be new architectures coming out all the time. There was also the use of CNNs, of the convolutional neural networks that were explored. So the transformer model, if you start with a recurrent neural network with attention, it's actually not a big jump to that. It's basically saying, okay, instead of just having attention to the source sentence, let's also have attention to the sentence itself and replace the recurrent element. The recurrent element has a bit of advantage that anything that is very far away has to jump through all these steps to actually arrive here. So if there's a word in a context very far away, it's very hard for it to influence the decisions down the road. The transformer model made this much easier because it paid attention to all the words in context. So that was really great. So if you look at the transformer paper, it's an MT paper. It uses our WMT test sets. And yeah, the reason why jargon terms like decoder-only large language models are now being used, it's really just because it's a transformer model which had an encoder and a decoder. And at some point, actually took them a while, large language models folks realized they don't need an encoder. So we have a single word string by trying to model. So why do you need an encoder?
Yeah. Can I just inject a comment?
Yeah, sure.
Yeah. So one is that there's another jargon term, which is statistical machine translation.
Yeah.
Since LLMs are also statistical machine translation.
Yeah. There was some,
nets are statistical devices.
Yeah, there were some holdouts who say like neural machine translation is also just statistical machine translation.
So this is just history. The other comment was that I always have to explain to people that like when they think of a language model, the language model was originally part of a speech system or later a machine translation system. It was only meant to break ties among things that the acoustic model proposed or the translation model proposed. It was breaking ties. Like what's happening now is like if you took the cooling system out of a car and you found that it could drive all by itself, like you just put it on the road and the fan belt is making it go along. That's like, these were not supposed to be working by themselves. It's just they got good enough. You didn't even have it. But originally, they were only breaking ties in a low entropy setting where you had an input.
Yeah, I thought they were a really important component. So
like
previously, the separation was really another way to put it. The translation models are like, oh, the translation has to have these words in it. I don't know how to put them together because language is different word order. And the language model figures out not only how to put them together in a coherent way, but also maybe this ambiguity.
I think it's also about influence or perhaps like the corpus system, because like the language model can't override the acoustic ones. It's like
it can, yeah. Sorry, I was just trying to pick something that had a moving part. It has a fan belt and a water pump and stuff. But yeah,
so then
we got to fix my analogy.
Then the analogy makes a little more sense because eventually your driver system can, like you can imagine it being so good that it takes over the driver.
That's a good analogy.
RNNs and transformers have kind of specific ways of dealing with variable length input. But how did those earlier n-gram language models do that?
They had, just like the statistical n-gram models before, they only had an n-gram window. So they cut off the history after.
Right.
And that was the biggest qualitative change that you noticed with neural models was that they actually built grammatically correct sentences. So before, an n-gram language model, you often like, it sounds nice, and then suddenly, oh, there's the end of the sentence. Where's the verb? Because it didn't really build a coherent sentence. So that's actually the one part where the syntax-based statistical models were very successful, because that was, you had to build now a syntax tree of the target sentence. And therefore you had to build a grammatically correct sentence. So that was already achieved to some degree with syntax-based. But a pure n-gram based model was always, it always flew nicely. It was a nice flow to it, but on a whole sentence level, the sentence often was not very grammatical.
I'll point out also that the n-gram language model, there was a Gamma Kuhn paper from the 90s, and then it came back into the field in the 2011 paper, which was Ashish Vaswani was one of the big ones then, which is, of course, the 2017 paper. And the 2013-2014 paper is an ACL Best paper by Jacob Devlin, as in the Bird paper. So it's actually these people that with the really famous papers had early ones also in the field.
Okay, so this was a chart I put together that got pretty famous, which tracked the performance of the models based on different amounts of data. So this is basically built English to Spanish systems for some reason, that language pair, I don't remember now why. And we put this is kind of a log scale. So each new data point, you have twice as much data. So the way we build this, we use all the data. So that's the last points. And then we halve the amount of data. And a surprising thing, so there's the green one is the neural models, which are very different core from the blue models. So the blue models are statistical models. The light blue one is somewhat a fair comparison because it was trained in exactly the same data on just the parallel text. And the dark blue one is how you actually would build a statistical model with a really, really large language model. So just to give you some numbers, the translation model typically was trained on 50 million, 100 million, that kind of number of words. And then the language model was trained on billions of words. That's kind of the models. So, yeah.
Is this a lot narrower now? Like, do you think, like with modern or the recent training techniques and regularization?
I think there has been some progress on the low end of these models. But yeah, the striking thing was clearly, the neural models only really work if you have lots of data. But then they kind of keep working, getting better. They can still take advantage of more and more data, which was then also seen years later with large language models that the bigger you make them, the better. So to the point that now you train them on 10,000 GPUs for 3 months and you build trillion parameter models.
Tuan Nguyen did his dissertation basically trying to answer your question, and it was trying to push the green curve as far to the left. So he has a whole dissertation on trend. So it does push the left. It doesn't completely hit it.
Okay.
Yeah, push the left. He has a whole dissertation on it.
Yeah, there's a bunch of interesting comments to make because the transformer, like typically you would think there's a new technology, let's try it on a small data set. But the transformer model actually, for instance, and even the recurrent neural network model, where they introduced that model, it was trained on French English, the largest data set language pair we had. And it was built on massive amount of data. And interestingly, if they would have tried a smaller amount of data, they might have been discouraged of doing it. The other thing that I think already snuck in here, so the lesson that monolingual data is a useful thing that we knew really well, then kind of got forgotten for a while or not really paid attention to. There were very little efforts to add monolingual data to neural machine translation models. Technique that we used was back translation, but we didn't add that much, not to the quantities that we used. Okay, so the latest development is that, finally, we also had to join the bandwagon of we're just adapting large language models. It took a while. I think it was really just like the last 1 or 2 years where that clearly has been established as a better method. The reason we held out longer with just building standalone models on our data was that for translation, you actually have a lot of data. You have 0.1 billion word parallel corpora. So you can train really good models on that.
You can use parallel corpora to tune LLMs as well.
Yeah, so here it is now, I'll go to how they're trained in a second. The big insight of why are we using large language models now instead of building them from scratch? It's like, yeah, maybe monolingual data is useful. We kind of knew that. We used language models, trained on monolingual data as a main component as part of it. Couple of comments on, there were initially some claims that large language models just learn machine translation as one of these emergent features. I thought they were really true. So the training data that these models are trained on have a lot of also parallel text in it. And it's definitely not true now because the language models are all explicitly trained on parallel data as well. Another thing to point out, so a lot of the things that are now the standard techniques in large language models actually come out of machine translation research. So already mentioned transformer model, bytecode encoding was introduced from machine translation. Various data synthesis methods like back translation. Minimum base risk decoding got resurrected. If you don't know what that is, that's my statement here. Still not really used in large language models. I think there's still some ideas in the history that haven't really been applied to large language models. So here's now the standard recipe to answer your question. So you take a big large language model, which are now called foundation models. Apparently now they're called frontier models. Latest jargon is. And then you also train a lot of monolingual text in the languages you care about. And then you train it additionally on a lot of parallel text in the language you care about. And then there's also a preference training strategy where you have alternative ways to kind of optimize the translation performance. Okay, stepping back a bit. So one of the drivers of this field was also that we had a fairly open environment to do research. So been running this sequence of things we originally called workshop and then started to call conference. So 10 versions as workshop now. 10 versions as conference, where we had each year kind of a proper evaluation. We had a test set that was created for that competition. So nobody had access to it. So we actually took text, very recent published news stories originally, hired translators to translate it. So it's a manually created test set, blind to the participants. That's what we evaluated on. What I also always liked about these things is that people wrote them system description papers and they were always very honest. So in a research paper, you have to say, we use this new method. It's so great. Look at all these results. In the system description paper, it didn't, you got a score. And then you describe what you did. And then you say, the great thing I talked about last year, I actually didn't use. So they were always much more honest. The idea we always had for these competitions that anybody should be able to participate. It was always the graduate student with a regular computer should be able to build a system. I'm not entirely sure where we are with that now. So we at Hopkins ourselves haven't really participated in these competitions in a while. But what I heard though is that you can build a pretty competitive system by adapting a large language model with the parallel data that's out there. And it's the order of maybe dozens of GPU hours or something like this, maybe 100 GPU hours. So it's still possible to build a pretty competitive system.
Can you say something about the languages in these competitions, like high resource, low resource?
It's a fairly broad mix. So we started out with high resource languages, was at the beginning very much focused on Europarl. It was also very driven by European funding. So we had German, French, Spanish, Czech. That was always good. We still have, from those, we still have German and Czech around. But we also have Chinese, Japanese. A lot of this is like someone needs to fund the translation of the test set. And this involves now a lot of different people who are willing to chip in. So that drives a bit the language choice. But we also have low resource languages. I say Maasai was one of them. I don't know. They were also really low resource African.
WMD 24++ covers 50 languages, and around 10 of them are fairly low resource. Around 10 of them, I would say that
12 of 50.
Yeah.
It covers 50 languages.
Yeah,
but that's
so
that's an extension of our test set. But the actual competition is about a dozen languages, and there's some low resource. There was also always to do a non-English centric pair or language pair without. I think this year we're gonna have, we had like German French for a while, we had like Czech Ukrainian, like this.
And these are all written languages, is that right?
It's all
So it's not speech translation.
yeah.
It's
This
not
was
sign
always
language
the
translation.
written translation task, although slowly.
Oh, that's good.
But not moving to speech, but not sign language.
Not sign language, definitely not.
And
There were separate tasks for sign language. There was always other.
So for speech recognition, we usually have very specific answer, but for translation, the same sentence might have several different. Maybe we'll go to evaluation later.
I'll talk about evaluation in a second.
Quick question. So the definition of low resource language kept shifting. Is there a current definition?
I don't think there's a current definition. Give you a bit of a sense. I think serious attempts to do text translation exist for maybe 200, 250 languages. After that, you kind of reach the point of languages that are maybe spoken a lot but not written very much, so you don't really find much text in them. So the other number you probably gonna hear is the Bible is translated into 1,600 languages. I'm not entirely sure what that means. It really just means maybe some missionary went somewhere and translated the Bible in the language, in a writing system he made up. That is not used by anybody. So low resource for text MT is around 200 languages. So tail end. Although there are always efforts to do translation for even lower resources. Okay. So data resources we had always publicly available. So it started out with like European Parliament proceedings. That was very easy to gather. A fairly large corpus, like 50 million words, was actually pretty useful for news translation. So although it's like speeches given in Parliament, we could actually build a really good news translation system. There's something called Opus that collected all kinds of parallel corpora and makes it publicly available. We were one of the earliest users of Common Crawl as a source for not just multilingual data, but also parallel data. We had a big project a few years ago called Paracrawl, where we just mined the web for parallel data. So there is a lot of, basically all the data that is kind of people use to build systems is all publicly available. Also, the software was always publicly available. So back in the days, something called Moses, which was an open source system that was used by everybody, including companies, so even Amazon actually used it. And nowadays, that is quite popular. So I think it also established this culture of open source tools. So definitely, for instance, proof that if you kept the code for your system to yourself, nobody cares. Nobody cares about your system. Nobody signs your paper. But if you give everything away, everybody uses that. Everybody writes the paper that their stuff is better than yours, but they still sign your paper. So here's my evaluation, long answer. This field has been obsessed with evaluation more than I would have done. So alongside, for instance, this translation task, there was also always a metrics task. So we actually already had this nice setup where we had systems, we had the output, we had human judgment, we always did human evaluation. So we actually had humans ranking the different translations. So now the metrics task had a perfect setup where you try to predict the human ranking. So if you can predict the human ranking, you had a better metric. So it was all the metrics task was evaluated on correlation with human metrics. And so it's a bit of a hard problem because there are many different ways you can translate sentences. Even long discussions about how to do human evaluation, it's not as simple as you think. It's not like someone looks at the translation and some people say it's great, sometimes it's terrible. There's not really much agreement. There's also, we did various different things, for instance, separating did the meaning get translated, that's adequacy, or is the output fluent output, that's fluency. Then we moved to this. It's hard to come up with absolute scores. So let's just show people two translations and ask them which one is better. Use that for a long time. And then we went back to kind of absolute scoring on a 100-point scale with like a ruler that you can then normalize. So some people on average are here, some people on average are there. So you can fix that. There's something called MQM ESL, which is now much more fine-grained error categories where people identify this word is wrong and this phrase is wrong and this is a major error, a smaller error, and so on and so on. So every year there's some change in how we do human evaluation. I already mentioned. There's also a long evaluation of automatic metrics. So the blur score was just kind of matching the output of the reference translation in some way, various variants of that. The latest thing is just train metrics directly on this data we created this way, because we have now a lot of human judgment data. So all you have to do is train a model that predicts the human judgment based on gigantic, deep, large language models, essentially. Anyway, so what helped this whole field along is always that you had new tests that every year manually created that didn't overlap with training data, which is not the case for a lot of with wider AI. Okay. Another thing we were always very aware of too, and I think it's a good recommendation, is to stay somewhat humble. So there was always hype, various hype cycles. So there's a completely made up chart of various hypes about MT. So the earliest happened already in the 1950s, where there was, you can watch old YouTube reels of the Georgetown experiment, where people use electronic brains, the size of refrigerators, to translate Russian into English. And they have a system, and it works currently on 100 words and has 5 grammar rules. But in 5 years, it's going to replace all translators. And this field was burned several times that way, that people made great promises, but then didn't deliver. So when we were around, you were always kind of like, yeah, it's gonna be good enough for something. It's gonna be good. Like, no, it's not going to change. We replace translators. There was a bit of a cultural shift when the deep learning people moved in and like literally wrote the paper immediately. Human parity, it's solved. Let's move on to the next thing. Which, it's still not really solved.
So a question is, so first of all, I'm very impressed by this graph. Collecting the data must have taken a lot of work. But I wonder actually if the hype has sometimes caused the reality to catch up.
Yeah.
Like you see here that the hype goes up,
Yeah.
maybe that attracts investment, and that's why the reality catches up, and there's a causal effect.
Yeah.
I don't know what you think.
I don't know how related the hype. I mean, the hype. What does the hype do? It brings people to the field. And more
It brings
work.
people, and maybe it brings funding.
Yeah.
Investment of two kinds.
Yeah.
I'd be interested in knowing how.
My reality curve is very flat here. It's totally but yeah.
I'd be interested in knowing how researchers, how persistent they are in the field through these dips. Like whether you have people who are basically like going through, they're weathering the storm. Still there, just kind of doing the same thing because they still believe in what they're doing.
I think there are different stories. I think the MT community was always fairly coherent and for a long time had pretty stable funding. It's really just dried up in the last 4 or 5 years. And people moved to adjacent fields. But yeah, historically, there was definitely, like when I got in the field around 2000, hardly anybody worked on TNS.
What does this reality curve mean?
Just how effective the technology really is. So, I mean, to give you some examples, I said like mid-2010, suddenly translators were faster by post-editing MT. They're translating from scratch. That was not the case before. I think the first time I saw it was like 6-7 years ago. We traveled abroad and people pull out Google Translate to communicate. That didn't exist. So,
and Philip, what was the inflection point in 1999 that caused that change in reality?
This is how drawn is drawn and involved.
Philipp became, yeah.
Yeah, I got involved in everything with that. I want to say that around 2000, there was still the field that MT doesn't work. That was definitely the consensus of everybody. MT doesn't work. And yeah, the first successful application were probably things like Google Translate. They couldn't go to a web page and translate it, and was maybe crummy and questionable, but at least you knew what it was about, and maybe you got the information you needed. I think that's the lowest bar for MT, that the meaning roughly comes across for someone who knows something about the subject.
When was Pharaoh initially? 99, please?
Also 2002.
It was 2000.
Yeah, phrase space was like
I don't know if that would be the jump.
that is the
David.
yeah that. I don't know. I didn't notice that. Steep jump. Okay. Anyway, it's a made up.
What's the reason do you think the transformer was initially proposed for machine translation but not for other tasks?
Mhm.
What was the reason do you think that transformer initial?
I think a lot. Well, it's a. I mean, the nice thing about machine translation was always a very clearly defined problem. To some degree, I mean, yes, you translate things in many different ways, but it's definitely much different from other NLP tasks where evaluation and data was always a huge problem. So if you think about summarization, people can about question answering, they all kind of rely on people then making up their own test set and their own particular scenario, and it's all artificial data that was kind of generated with that. This is kind of a naturally occurring task with billions of words of training data. So it was just ready to work on. It's very easy to then build something for it. You have the data, you have stuff, evaluation protocols. So it was just a good NLP task to work on.
Ashish Vaswani also has a PhD in machine translation.
Yeah.
So
yeah. Okay. This took much longer than I thought. So I think the only okay, I'll go over this talk. This is active research I'm doing with Iraq right now on expressive speech translation. So let me talk about that. So first of all, there's people here who don't know speech, and I didn't know speech for a while either. This is the pictures I always saw by people who talk about speech. Very colorful, very confusing. But the way you look at them is so sound comes out of mouth, and there are low frequencies and high frequencies. So he and so these are the different frequencies, and in the picture at the bottom, they kind of split up. I don't know actually what's high, what's low. Probably what's up, it's high. And then there's specific loudness at various frequencies. So if you say something, it then is a mix of all these loudness at various frequencies. So in the picture, all the kind of lighter color, yellowish, greenish, bits where it's a bit louder. And I should probably quiz some of the speech people here. Can you actually read from that what it says? I know Matthew, the reason I knew that. Like, oh, that's an F. Because you have like, you can imagine like sort of like, so you have loudness and then suddenly it drops off. But there's also like this, so that all these have like characteristic kind of,
fricatives.
yeah, things like that. So like, anyway, so that's a speech signal. So this is very messy. I mean, we use text, words. You can see we're tokenize it. Then it's just one thing. This is definitely much here. So the first thing that's been done is kind of, so you segment that into, discrete pieces called frames. So I'm saying here 50 frames per second. And then you actually already at a sequence of things. So we're a bit more comfortable with that. Here's my one slide about what makes speech hard. The first of all is that spoken language is very ungrammatical. So if you spontaneously speak, you're not going to say many actually properly grammatical sentences. You also have restarts, repetition, pauses, filler words. There's also noise in the background. I've been here and heard about whole thesis presentation on reverberation, which is the echo in the room. There's a lot of discussion of the cocktail party effect, which is a fascinating thing. If you're in a room full of people and they all talk, people are very good at honing in on one person and just listening to them, that one person, even if like 5 people talk over them at the same time. Machines have a really hard time with that, or used to at least. Then there's a lot of how do you actually record that, and like which frequencies get filtered out. For instance, if you have a conversation over telephone, probably still in today's telephone networks, but definitely 30, 40 years ago, a lot of frequencies were just filtered out because they're not needed. And where the microphone is placed, maybe there are even multiple microphones. More linguistically, there's also much more variety in how people speak. So everybody has a distinct voice. So everybody sounds a bit different. So each person speaks sounds differently. But there's also more language varieties. If you think about English as a written language, is fairly standardized. Even people in Britain adding extra U's, don't know how to put R and E's in the right order. But the spoken language is actually much more varied to the point of you can probably go to some places in the countryside and have no idea what the people are talking about. There's also more information in the speech signal. So there's tone, emotional content, which is actually fairly important. So if you actually have a conversation with someone, very often you care about are they paying attention to me? Do they understand what I'm saying? Do they agree with me? That is much clearer in the speech than in the text. So you probably have the experience if you communicate in a chat room, you make a joke, nobody understands the joke, everybody's angry at you. That doesn't happen so much in speech because it's clear from the tone of your voice of your joke. Interestingly, also, there's less data, which is on the one hand surprising because people definitely speak more than they write. But then when they write, it's written down, so it's preserved. When they speak, it's not always recorded. So we actually have much less data. Okay, a little bit make things more comfortable for us. A standard technique that is now being used when you take speech, so you actually try to tokenize it. So it looks like a sequence of tokens, just like text looks like a sequence of tokens. So this is standard techniques of kind of taking the speech signal and tokenize it. There are two different types of tokens. One are called semantic tokens, which have the meaning, but it's really more to the level of granularity of which letter is being said or which vowel and consonant is being said at that point. And then the acoustic tokens can also have all the other elements of the speech signal, which is how something is said, at tone, how it is, so on and so on. So speech translation has been around forever. We at Hopkins have been working on speech translations also since whatever, 25, 30 years, maybe longer. The standard technique is always you have your speech group that does ASR, so it takes the inputs audio, turns it into text, and then you have your MT group that does the text translation. And sometimes you also want to generate output audio, not actually that one. But it's basically 3 different steps. And people have built these systems for a long, long time. So the critique for that is that it's error propagation whenever you screw. If you screw up the ASRs, you're going to have a mistake that carries through. It also slows down processing because maybe one step has to finish first because it's not the other step unless you want to have really complicated algorithms. Also, we actually have debates for data formats. So for some reason, speech world doesn't believe in punctuation or uppercase and lowercase. Number 5 is being said. They actually write F-I-V-E instead of the letter. Okay. So there's actually also some problems to kind of connect these. Okay, so the goal is a bit, or the dream is to move to end-to-end systems. So there are a lot of efforts in that area. It's still actually not clear if that's the best way to build a speech translation system at the moment. So at the moment, I think you still often do better with a cascaded system than an end-to-end system. One of the reasons is you just don't have the data. You don't have a lot of spoken language that is translated into spoken language. That data is extremely rare. The only place this data actually gets produced is either if you can get a hold of live interpretation at some kind of international event where people speak different languages. So people, for instance, gathered this stuff from European Parliament proceedings. We try to get some data from UN live translations. And the other area where that happens is the dubbing of movies and TV shows, which is then all very copyrighted, very hard to get hold of. Anyway, but still also in quantities, very, very small. While for the other kinds of things, we actually have much more data. We have comparably massive amounts of text translation data, and there's also still a lot of good, large amounts of text transcription data, either dedicated for built for this, but often also just semi-naturally occurring, where people have YouTube videos and then there's a manually curated. Yeah.
How about movies and audiobooks that are available in many languages?
Yeah, so we actually collecting all that data and try to mine that data. It's just not that many. And available also means it's an out of copyright, so it's really just Charles Dickens stuff, not the latest things, because all those are copyrighted as well. Yeah. Yeah,
I don't actually know what the fair use requirements are. Like, I could imagine that if you had a partnership with Amazon, which has like a huge film library, including dub tracks in many languages, and they have I guess they have Audible as well, so they have this huge audiobook library. So is it really not fair to train on that stuff? Like, it's not being used to produce the original works. It's only being used to translate new stuff.
Yeah, so I have opinions about this that I might not want to say in a live recording, but I also know
I just
like even
the FBI coming for me.
But even in companies, they might not even be able to do that. So actually, I heard a news story 2 days ago that the German the live interpreter, basically the people who dubbed movies into German, they are on strike with Netflix because Netflix wants them to sign that they can use their data to train AI models. They don't want to sign that.
Yep.
So apparently they previously didn't have these signatures and therefore can't legally even use their own data that they have. So yeah.
Interesting.
Okay, I need to make some kind of progress. So how do you get the data? So the standard technique is really just you kind of create the data by synthesizing the pieces you don't have. So if you have parallel text, you can run speech synthesis on both the source and the target language, and that gives you parallel data. Or you have transcribed speech, you can then run that to the NP system. So we have worked on that. Many people here have worked on that. Papers on those kind of techniques. The other technique is to kind of build on top of existing models and make them better and better. So if you start with a large language model, it knows basically this is trained on all the text. So it's a very good text model. So it knows a lot about semantics, and then you extend that model by make it also accept speech input instead of text input. So now you train it on transcription data, but maybe also speech translation data or any other kind of speech task you can think of. So you build on something you already have and add additional components, and then also do that on the target side to let the models produce. So this is a very active area right now, how to actually build really good speech language models, or even broader audio language models that also take any kind of noise and ask questions about what it says. This is a car driving down the road. Okay, so we're interested in expressive speech translation, where we not only want to translate what is being said, but also how it's being said. So when we generate the speech in the output, it should have exactly the same prosodic nuance than the speech in the input. So here's one example. So you can read that any way you want, but it could be enthusiastic, yeah, really. Or it could be very skeptical, yeah, really. Or annoyed, or it could mean all kinds of things. And when you translate that, already the text translation might actually look quite different. But in a speech translation, you want to preserve that as well. So it should sound the same, the target. And it might not only be as a utterance wide, but also tied to particular words. So here's an example of how you could say the sentence in many different ways. So the first one is, I think I would not do it that way, which is skepticism, but also I'm not super sure. Maybe it's a good idea, but I might not do it that way. Or what's the last one? I think I would not do it that way, which is like, it's good to do it, but don't do it that way. So all these mean different things. So they all have very different intent, and therefore you want to preserve that when you translate them. Okay, so what's prosody? So I already mentioned that. someone should correct me on that slide probably. So the first thing is, maybe that's not even prosody. So the speaker's identity, so that's my voice, so the translation that sounds like my voice. Going back to data, that data basically doesn't exist. So even the best data you can get, like dubbing data, it's a different speaker. You have a different speaker for the different languages. They try to match everything else, but it's a different voice. There's something called timbre, which I forgot what it was. Emotion, acoustic conditions, and more on the word level. So there's pitch, so as the voice goes up or goes down. The energy, if you say something loud, suddenly quiet again. Speed, how fast you pronounce each word, and then pauses. Yeah.
So presumably you don't want to preserve pitch when it serves a different function, right? So the intonation contours will differ, and when you're translating Chinese to English, you want to drop the tones instead of preserving the tones while still keeping the prosodic contours, right?
Yeah, pitch gets a bit messy because there's some languages, for instance, tonal languages, where pitch actually means something. But there's still a difference between like saying something in an angry voice and a calm voice, and the pitch is different. That's one of the indicators of that.
But the prosodic contour for a low-rise question that you sometimes see in English, I think that contour doesn't show up in all languages for questions.
Yeah, it doesn't show up in all languages. So that there are some language-specific things. So the best thing I know about this, there was a paper 2 years ago from one of our former students, Brian Thompson, who at Amazon looked at dubbing data and just see how well these things match.
Right.
And I think he found that things like energy, so how loud everything is, matches the best, but also pitch matches actually well. The dubbed versions. So. Okay, so we basically want to preserve all these things in translation. So there's various ways you can extract these different things. So this is here, pitch, contour. Someone currently working on that with us on how to do that. Emotion is kind of an interesting thing to bring up because it's the obvious thing you want to preserve, but then it's one of these folk psychology terms that don't really have a very precise meaning. So a very, very simplistic view of emotion is that there are like two aspects to it. You have the unpleasant and pleasant, and then low and high energy arousal. So then you can kind of pitch every emotion somewhat into that chart. So if you have whatever, top is neither unpleasant or pleasant, but astonished, like ooh. Wow, see like high voice, very loud, so on. Things like this. Sleepy. I'm not gonna imitate. You're already laughing too much.
I just like your love of performance spell. You're a good actor.
Oh, yeah, I could.
Okay, we're moving on. So this is the model I am currently working on. So the first thing we want to do is build a cascaded system that does this. So basically takes a speech signal, that's from speech recognition, but also identifies individual words, gets word level speech features for all these words, and then have a generation process that synthesizes output speech from the text translation of these words, but also maps each word back to its prosodic, to its source word, therefore can copy or map, not clear at the moment, that prosodic information to then produce basically output in the same kind of prosodic things. So there's both at the bottom, you see the word level features, at top kind of the global speech features, which is the speaker's voice overall.
Does it have to be prosodic to prosodic, or can it also cross over into like the text of the translation, the prosodic information?
Yeah, so here we kind of separate text translation from the speech translation, but you could imagine you could inform the machine translation by additional speech input. But yeah, so this is the yeah, great. Just what is it? Yeah, right example. But yeah, their hope is mostly that the text translation should change much. The prosody gives you that additional information.
And where do you put the prosody related consistent constraint to this structure? If we want to keep the consistency of the prosody and etc., where for your current structure, we'll put such release the laws, etc. to some. Like,
Yeah, so training and everything is a bit tricky, but so we basically train a separate speech synthesis system that takes as input the words and the prosodic information for each word and generates speech.
And prosodic.
And we have probably some reference speech, how it should sound like, and how to evaluate that it's the same thing. Yeah, so there are prosodic metrics that measure that. You can basically even measure pitch and speech, see how well it matches up. But evaluation of speech synthesis is generally really tricky. It's like this dual goals of it should be understandable and the words should be clearly, but then the desired prosodic properties also need to come through in their spectrum.
Philip, how much are prosodic contours robust between languages? So we rise tone in cases of doubt, really, or whatever. But are those robust across languages?
So as I said, there was this one study on dubbing data, and we are currently working on that as well. So we basically obtained also some dubbing data and doing basically this kind of analysis at the moment, how well it translates. So I'll have a better answer in a few months. So.
And when you do conversion from prosody into syntax, how often, like for example, stress or emphasis might be a reorder in free order languages to front with the more stressed condition. Do you have features you're considering for how you capture things like stress from prosody into syntax?
Yeah, also like reordering does throw a little bit of wrench into this whole thing because there's also overflow to it. And if you reorder it, then that gets broken out. I don't have a good answer to that at the moment. Okay.
Yeah, so it seems to me that in speech translation, maybe the linguistic variables are actually useful. And so including them as auxiliary tasks could help with explaining away. I don't know, maybe you already have enough pre-training to be able to discover the linguistic variables automatically. But
I'm not sure if I fully understand.
So sometimes the prosody is dictated by syntactic structure, and the syntactic structure gets changed in the translation. And so the prosody changes accordingly. Like it's not that you have a pause after a particular word, it's that you have a pause after a particular noun phrase, and it ends not in a translation of that word, but a translation of some other word because there is reordering. And so I wonder whether there's any room for linguistics to play a role, especially given the smaller amount of data that you're dealing with.
Yeah, so I think there's definitely a lot of room to figure out exactly how prosody matches between languages. And the best data we have to study that is kind of dubbing data, where it's very expressive because people with movies are really more excited than background.
They overact.
And people to really try to preserve that because they also have to match kind of facial expressions, speaker.
Yeah, just a comment. I would imagine that the geography as well is important. Like if you were, I don't know, speak Spanish in Latin America, it could mean like depending how you say it, could mean really different things. Or like in Australia, you say yeah, nah, it actually means yeah. Like so.
My character is always between Finnish and Italian, where some languages things like blah blah blah. Let's get married. Okay, sure. Where in other languages.
About the study of emotion, both sides are very important.
Okay, I'm basically I'm halfway through the talk. I'm not going to finish the talk. What else do you want to say about that? That's all I'm interesting. Okay, let me just quickly say like 5 minutes about something else I'm working on, which is basically, so here's actually a good example. So if I ask this here in English, what did I ask here? ChatGPT, universities I studied, and it's all correct. And then I asked the same question in Chinese. And no, I wasn't university. First of all, I can't read any of that, but it's all. I was never at the University of Vienna or TU Wien and things like this. So I think I translated that. No, I not. I actually don't have machine translation back into English, but clearly it doesn't do that. So it's basically the same model. You ask it in different languages, you get different responses. That shouldn't happen. So here's one other analysis of how good the models are and tries to map it against the number of speakers of the language. And there's clearly some correlation, but it's not perfect. So basically, this is something I was smaller role in also organizing was at WMT, we had a multilingual instruction following task. We had like various tasks and we post in a different language, try to make that work. Basically check how current models are doing things in languages. From the colors, at least, it suggests that it's doing better for some languages. I think that's all I'm gonna say about this. So maybe I should say this. The reason why this is to a large degree there's so much more data in English than for other languages. And it's hard to address that. So simple oversampling and undersampling creates very crazy training dynamics that you then overfit on the low resource data while you're not underfit on the English data. Anyway, that's another interesting topic I don't have time for today. So Ken and I just submit an NSF proposal for this topic. So it's not interesting. With that. Okay, I'll stop here.
Questions on my website.
Topic radio is interesting. So we actually had a paper where we collected radio data.
It's like you aren't just like calculating how many papers. Do it. So you expect that delta.
Sorry.
You automatically have that delta.
You can test that.
It's like maybe that's yeah.
So